the same account said
right, Tanya, can you unmute yourself and say, bring up the issue that you...
Oh, hey, yeah, that was actually me, Tanya. It was mostly an answer to the comment that came up in the Q&A before when I was talking about, that was not me, numbers have been factored. Somebody wrote in the chat, I presume, but I didn't see it, but Shafi, you read it out, that D-Wave is factoring large numbers. And so I pasted a link to the paper, which is showing that the D-Wave approach can't actually get big speed ups. They're trying to do something about set solvers. So it was more an answer than a question. I can paste the link here as well if you want.
So this is something that you posted on the chat of the talk?
Give me a sec.
Somebody
is there a way to access the chat now that the talk is over?
No, because you know what? Maybe somebody recorded it. Hold on.
You probably will get an email afterwards with the chat log, but I mean the host.
Yeah. But anyway, now I got a pointer from Tanya on the new chat.
Yeah. So here's the link to the archive paper. But I mean that's specific to the D-Wave thing. And I think that was a very small aside. I mean, Daniele, you were nicely motivating the whole area by saying a factoring will be broken in the future, but not quite yet. And I totally agree with that statement.
So we are getting closer.
Sure, but I don't think that the D-Wave thing is getting us anywhere closer.
It is not.
It's nothing which gives you a exponential speed up. I mean,
yeah.
So in Shor's algorithm brings it down to polynomial time, and this one is not getting much.
I mean, SAT solving, it's NP complete. So we don't expect that to be polynomial time, but it can be a
exactly.
concrete speed up. I mean, even getting a concrete speed up over the best classical algorithm is non-trivial. So I take this as an indication that quantum computers, the threat of quantum computing for factoring-based cryptography is a real threat. I mean, it's not an immediate danger, but is a serious issue in the long run.
So one of the things that they were talking about in the chat, which again, I don't remember who it was, is that D-Wave is working currently about some approaches to subset sum, and I don't know what versions of subset sum. Hopefully,
but this could be, if you have methods to use these D-Wave machines for SAT solving to maybe speed up. I mean, so the same. Yeah, it's not surprising that the same could be used to speed up subset sum. But then, what you can achieve in the end, if you are targeting the NP-hard version of the problem, of course, is necessarily limited.
I was wondering if you can put up your slides with that you rushed through with the multiplication of version.
You mean now? I share them. Yeah, I can do that. But yeah, I'll just need to load the slides. Share. Oh, I see. I need to move them to a different window.
I think you say sharing or something. You share.
No, I know. The problem is that you can only share something that is showing on my screen. If I have multiple desktops, one of them is not showing, then Zoom doesn't see it. And I just needed to move a few windows around. Oh, now Zoom disappeared. Okay, let me move Zoom here. And no.
Does anybody else have more questions, or is it just between me and Daniele that don't understand the slides?
So I had a question regarding, so you explained 4 different ways of multiplication. So I wanted to know if there is some sort of inherent similarity between all these 4 methods, or these are conceptually different from each other. Like, are they sort of semantically equivalent in a mathematical sense, or are they just different, and there is no equivalence between them?
Yes and no, in the sense that addition is addition. So there's just one way to, so that the numbers are added in the same way. But the four methods, as far as I can tell, they are using this additivity in different ways. There are different methods to use the same additivity property. So it's not, so there are different schemes in the end. So that you're performing, the way you perform operations on the ciphertexts is somehow different. And this also is something that you can see that the result is different if you look at the security assumptions which they produce, and also the level of efficiency that they produce. So you can still think of them as different variants of the same very high level general idea of, oh, let's use the linearity property to do multiplication, but the linearity properties are used in ways that I think are genuinely different.
So if you can go back to the number three, method number 3.
You can see the slides now, correct?
Yes, we can.
Yeah.
So the previous method, in the second method, you're saying that you need super polynomial factors, right?
Mm-hmm.
Where does that come in? Due to what is it?
Oh, that's because, so the second method, each time you do a multiplication, the noise is growing by a certain amount. And before you perform enough operations to implement the bootstrapping, the noise has grown by a super polynomial amount.
And that does not happen. So that's why I wanted to look at method 3, where
method 3 supports. So in the second method, the noise growth is symmetric. So given two ciphertexts which have a certain amount of noise, you combine them together and you have an amount of noise that if you change the order of the two ciphertexts, you still get the same. So and if you look at the definition of the second method, it is the tensor product of two ciphertexts. So the operation itself is symmetric. So the third method is an operation to combine the two schemes. Is a method, it's not symmetric. It doesn't, if you use it to implement arbitrary circuits, also in that case, you can get super polynomial growth. But it happens that you can implement, you can give a specialized implementation of bootstrapping that when implemented using the third method, only require polynomial noise. Okay. Noise growth.
And that's from the GSW?
Yes, it is the GSW. I mean, what I described is a different perspective, is a different way to build the GSW in a sense. You can think of it as, so this multiplication by homomorphic decryption. So the way I like to present it is that you are decrypting, and so you're decrypting ciphertext 1 under a M2 multiple of the secret key. Mm. And that gives an encryption of M1, M2. Mm. But they are used in a very asymmetric way, the two ciphertexts. One is used as a decryption key, and the other one is used as an actual ciphertext being decrypted. I'm not sure which slides is best to illustrate.
So I don't know if anybody has questions about multiplication 3 because it went really quickly. So maybe anybody, because then I would move on to 4. Any questions? Any requests to see it in more detail?
There's a question.
I had an unrelated question. And then my question was, do you have a recommendation for a resource to know why lattices are resistant to quantum computing?
No, I think that's so that's a recurring question. People ask, oh, how do I know that people are even trying to do it? And as far as I can tell, people are trying, but unsuccessfully. And there's a problem that if you try to break them using quantum algorithms, and you fail, it's hard to publish a paper on that. So there's a sample bias. So you only get to see attacks when they work. And this is something I suggested sometime in the past. We should find a way to document also attempts by knowledgeable people that we know are expert in the area. So we should find a way so that even those attempts is something you can read about. Now, so there are a few papers out there that somehow use quantum to achieve something in the lattice setting, but it's very, very limited right now, and there is very little to read. But most importantly, you are asking, what should I read to know that it doesn't work? And no, it didn't get written. So whatever, I didn't try. That's not one of the things that I've been working on personally, but I know people that tried to do it. In some cases, they even came up with candidate solutions and algorithms, which at a closer look turned out to be wrong, incorrect. And I mean, I don't think there is anything to be ashamed about. You try to do something and it doesn't work. Even the insight that you get from doing that would be interesting for many people to read, but it's just very hard for this type of work to get documented. So I don't know if anybody else in the audience has, or at the Simons Institute, has other suggestions about how we could address this.
It looks like Noah does.
Yeah. Well, okay. Actually, I have a response to the original question, which is just like, what would be more surprising is a quantum attack that's not a classical attack, right? Like there aren't that many examples of things that quantum computers give exponential speedups for. So like in some sense, we're kind of biased because it happens to be the case that factoring and discrete log are some of those few examples, but in general, like we shouldn't expect that. And also just another example of a failed algorithm, quantum algorithm for lattice problems is Oded's LWE reduction, right? I mean, that was the original purpose of it, was to find an efficient quantum algorithm. So like people have been thinking about it since at least, when Oded was working on that in the 2000s.
So there's another question here in the chat. Could we hope for a truly practical scheme by finding the right algebraic lattice, right in quotes, or have we exhausted our search on space to define lattices? E.g. torus FGE tried to do that. I could even ask for the right algebraic lattices for specific applications, such as running statistics on data. Interesting.
So yeah, well, it depends what you mean by truly practical. In some sense, we already have truly practical schemes. For some definition of truly practical is something that you can run. Yes, there are schemes that you can run, and as you mentioned, there are libraries implementing these schemes. Now, TFHE is using encryption of the torus. I don't think that using the torus makes any difference. Whatever is achieved by that scheme can also be achieved without using the torus. So sometimes just looking at things in terms of efficiency doesn't necessarily provide the best understanding, but there are certainly reasonable candidates that are being considered for use on the application side. I'm not an expert when it comes to applications.
So I think maybe extending that question, the question is, can you in some sense almost have a compiler that would say that for a particular application, one kind of multiplication, say, they're talking about one kind of a crypto system or lattice, but one can even ask that about specific multiplication methods. Can you sort of semi-automatically decide which is the right multiplication to use for an application?
In principle, yes, but and in fact, there are even some projects trying to attempt to do that. But right now, even providing a good, description taxonomy of the various techniques in a modular way so that you can more easily mix and match different schemes is something that is not that easy to extract from the published literature. So it's sure it can be done, but there is work to be done to get there.
Okay, any more questions? Otherwise, I'd love it if you moved on to multiplication 4, and we won't keep you past 12:30. Any more questions? Okay. So when you propose this, one of my questions was, you were suggesting it in the context of bootstrapping.
Mm-hmm. So the idea of this method 4, which was proposed in the few scheme, is that in some bootstrapping procedures, specifically in the bootstrapping procedures based on GSW, so this starting from the work of Zvika and Vinod at ITCS 2014. That was the first scheme that achieved bootstrapping with polynomial approximation factor. Now, those bootstrapping procedures also allow the computation of pretty much arbitrary functions on the ciphertext that is being bootstrapped. Now, so this is not as, when I say arbitrary functions, you have to keep in mind that you are bootstrapping a single ciphertext. So it's not, that doesn't give you FHE, the fact that you can compute arbitrary functions for free. So, but what you can do is to use addition to combine ciphertext 1 and ciphertext 2 into a single one. And then during bootstrapping, you can apply an arbitrary function on C. And there is this combination of binary addition and computation of arbitrary unary functions that when put together allow to perform arbitrary computations. For example, addition modulo 4 and division by 2 with rounding. So that's enough to implement all binary gates. So that's the...
Right.
Yeah.
Okay.
So it's basically, so the idea of pushing some of the computation inside the bootstrapping procedure is one of the key elements, and that's what I call gate bootstrapping. It is something that now is being used also in there are a few other more recent papers using this idea of pushing computation in the gate. For example, the TFH scheme is using the same type of multiplication by addition, and then doing division by 2 during bootstrapping. The difference is that in TFHE, well, on one hand, they are using real arithmetic instead of modulo Q, which I don't think has any impact on the, you just get the same results. I don't think it makes any difference, but they are using a different bootstrapping procedure than the one that was used in my paper. So you can think of that as an alternative method. So you could use the same method also to bootstrap a few ciphertexts. In fact, I have a recent paper on ePrint with Yuri Polyakov where we compare the two bootstrapping procedures in the context of few. And this idea of pushing some of the computation inside the bootstrapping also appears as being used in the Chimera paper, which shares some of the authors with TFHE, where they describe a method to convert between different FHE schemes. And so that's pretty standard, that you can use bootstrapping to go from one scheme to the other, but then they combine it with the idea is that as you convert one scheme into the other using bootstrapping, you can also throw some computation inside the bootstrapping procedure to get a conversion, which is also achieving something useful at the same time. So it improves performance. You can optimize the whole computation by pushing some of the computation inside the bootstrapping step.
Got it. Oh, excellent. Thank you. Any other questions? Anybody? So I think that maybe we could all unmute and clap for you. Thank you very much.
Thank you.
Great talk, and see you soon, guys. Tea or something, or.
Yep. Bye-bye.
Bye.
Is there a Lattice seminar tomorrow, Tuesday and Thursday?
Yes, there will be. I'm sending the email right now. It's at
okay,
11
it has not been announced yet, but there will be one. Okay, so I guess I'll see you then.
Perfect.
So,
Bye.
Goodbye.
I had a request.
Oh yeah.
Would it be possible to make these slides available as soon as possible so that we can?
Yeah. The slides are always. I think they're always posted at some point by Simon. I will send them right away to Simon and to Jesse, and I think they get posted on the website together with the talk, so they are easily. There will be a recording of the talk and the slides available there on that page.
Right.
I'll send them right away.
It would also be great if we can have the FAQ section also posted online.
What section?
The current FAQ section. The questions and answers.
The video.
Yeah.
Yeah. So I didn't record it, but I saw it was being recorded. So I think that that's why they recorded it, so that they can. I mean, it will require some stitching, putting the two videos together, but I think that's the plan.
Right.
Okay.
Okay.
Thanks. Bye, guys.
Thanks.
Bye.